Hello and welcome to the latest in the JSOA webinar series. Today's webinar is in cooperation with the Satcoms Innovation Group, or SIG. I'm Helen Whedon, I'm the Managing Director of SIG. For anyone that doesn't know, we're a technical industry group that brings together people from across the industry to solve common challenges. And we're working at the moment together with JSOA to look into flat panel antennas and moving the industry towards some sort of standardized approach. So that's where we're going to delve into this topic. So let me start by introducing our panelists. So we've got Jeremy Turpin, who is Chief Scientist and co-founder of Allspace. Angela Wheeler, Director of Global Network Operations at Intelsat. Then we have Joachim Espeland, CEO of QuadSat, and Harvinder Singh Nagy, who's Senior Systems Architect, Future Networks for the Satellite Applications Catapult. Welcome, everybody. Just to quickly introduce the topic a little bit, flat panel antennas. As you are mostly aware, there's a huge number of flat panel antennas already in the market, and more being introduced at quite an astounding pace. And that's great because these products are vital for the next generation of satellite communications, but they come with varying degrees of quality, and there's a risk, therefore, of causing errors, harmful interference. So how do we get to a point where we can have a more standardized approach, ensure that the operators have the data that they need to make the decisions for their networks? So that's what we're going to try and delve into. We're going to try and discuss the challenge, but also how we get to some sort of resolution. So first of all, I would just like to ask the panel to briefly introduce themselves and the companies that they're from. Maybe we can start with Harvinder.
Hi, Harvinder Nagy from Satellite Application Catapult, Future Networks. My role here is to help energize the market and look at different avenues and the national capabilities, and one of them is a capability called CSAT, which is comms on the move for next generation of electronically steerable antennas. So we're working on that. And previously, I've been in industry for about 29 years in SATCOM and aerospace sector, and obviously defense as well from time to time. That's me. Thank you.
Great, thank you, Harvinder. Jeremy, could you go next, please?
Hello, I'm Jeremy Turpin from Allspace. I'm responsible for next generation product planning and developing our capabilities to augment the first product that we're bringing to market here of our multi-link terminal.
Great. Angela?
Hi, Angela Wheeler from Intelsat. I lead our Global Network Operations Centers. We are responsible for supporting all services through the various Intelsat networks.
Thanks, Angela. And Joachim?
Hi, my name is Joachim Espeland. I am the CEO and co-founder at QuadSat. We help antenna manufacturers, satellite operators, and service companies basically test and make a smooth antenna qualification process using drone-based antenna test and measurement technology.
Great, thank you, everybody. So I'd like to start with a question for all of you to answer, just to kind of help set the scene. So from your experience, do you think we do face a potential problem with these flat panel antennas being allowed onto satellite networks too easily? So Jeremy, perhaps you could kick us off with that.
So my perspective, I suppose, maybe be different than Angela's. My concern is more, do we let them onto the networks with too much trouble, too much challenge? I don't believe I've seen operators be cavalier. Now, we've appreciated most of the folks we've worked with have been quite helpful in letting us on for test purposes and allowing us to learn about the terminal and demonstrate it to both our mutual customers. But all the experiences that we've had to date have been quite rigorous, and the operators have been very interested in the operation of the terminal. We are bringing a terminal to market that uses different physics, uses different operating principles than other terminals out there, and so it takes a bit of understanding, and it has its own characteristics. So from our perspective, we are very interested in trying to synchronize those requirements between operators and between different use cases, different regulatory regimes, such that we don't have to repeat measurements. We have had cases where one group of people ask us for one set of data that we go and capture and measure, and then someone else asks us for something on a different grid, perhaps that we didn't measure the first time, or asks us for data that is quite troublesome for us to obtain, and so it starts a lot of back and forth. Obviously, as a terminal vendor, we have a vested interest in getting our terminals onto these networks, which means that we are hence very interested in this conversation.
Great. Harvinder, what's your perspective on this?
My point, if the problem we face with a flat panel antenna being allowed into the satellite network, I'm looking at interference risks. If there is prematurely tested antennas being deployed in the field, and that hasn't been ratified by the operators, and the interferences is going to pose a threat to other network operators. Again, I mean, flat panel antennas being aggressively used, and it's kind of coming into the market at fairly high pace. I mean, lack of standardization is also another issue. There's some regulatory challenges as well. So we do work with Ofcom and other bodies, and there hasn't been enough policing efforts to be imposed on these as well. And then, if you bring into the field, which has got, the problems is the operational efficiency as well. So even though flat panel antennas do have a lot of benefits, but they do have challenges that things which parabolic antennas could offer, and that there is discrepancies. I mean, you can't have the same thing because these are fairly power hungry, and the thermal management issues as well. So there's a lot of aspects. That's me.
Thank you. So Joachim, how about you? What's your view?
I mean, with any technological progress, it is always a little bit of a challenge, and a flat panel is certainly a big technological step forward in the ground equipment for satellite communication. I like to look a little bit back on the TRL scale, the technology readiness scale, and if you at about 6 or 7 on a technological readiness scale, you need to start testing it in a real environment to move any further. And when you get up to, if you're going to get up to 9, you have to have it deployed in the market to get there, and you kind of need to manage it without ruining it for everybody else as you go. So I think that's a lot of the key thing here is to well manage the deployment in the beginning, because there will be things that you only will discover when the technology is rolled out as well. But of course, as Harvinder says as well, there are certain restrictions maybe that comes with flat panel antennas that you don't have with parabolic, and on the other side there are a lot of new opportunities that comes with it as well. So it's the area where you deploy it.
Thank you. So Angela, as the operator on the panel, what's your perspective?
So from a satellite operator perspective, we're looking at things from in a couple different ways, right? So one of the most important ways that we're looking at it is ensuring that the antennas that our customers are bringing to the table, or manufacturers are bringing to the table, meet the needs of the customers, and that's from several different perspectives. They have there's weight and power requirements and all those types of things, but of course the performance requirements are of our utmost concern. And when you look at some of the antennas that are coming into the market today, the performance can be quite challenging in the flat panel arena, not across the board. So when we're looking at that, we're looking to make sure that what antenna is being brought to the table for utilization meets the needs of the customer, but also meets the needs of the environment that it'll be transmitting into. And that we want to make sure that we're utilizing our bandwidth to the best efficiency possible while still meeting the customer's needs.
So, Jeremy, you touched a little bit on the sort of challenge of meeting those approvals. I wonder if you could go into a bit more detail about some of the challenges you're facing, both in terms of meeting antenna approvals with the operators and also in meeting perhaps the sort of end user requirements to some degree.
Certainly. The biggest challenge is that requirements and regulatory requirements have been written with the assumption, although not the requirement, of that everything's a parabolic, and there's a reason for that, of course. There's an assumption of fixed performance. There's an assumption of the ability to not have to worry about changes over time or over scan, and you can pretend that your flat panel antenna is a parabolic, but it means you have to throw away 90% of that terminal's performance, and you have to treat it at all times as if it is performing at its worst. And flat panels, phased arrays, and other similar structures, at their heart, they change their performance with frequency, with time, and with angle. And so Allspace's biggest challenge is finding the right way to work with our counterparts, with our vendors or customers or regulatory bodies in such a way that we can realize the benefits from the flat panel, from our terminals capability, without causing undue interference and while also not requiring too much capacity so that it's not a problem. We're have been quite successful in customer demand, and a lot of our technology has been developed with the assistance and with the cooperation of our future customers. So we are quite confident that the trade-offs that we're making in the design of the terminal are indeed meeting their needs, but we still have to figure out in practice, and still have to work out in practice with the operator, with the end users, how do they actually use the terminal. Cooperation with the modem, cooperation with capacity. How do you change between modes? How do you get the best out of the terminal at all points throughout its operating capacity? And during a small fraction of the time, you are going to be operating at the worst case. How can we avoid budgeting link budgets, or building capacity pricing, or building regulatory approval based solely upon that worst case? Similar, I'll talk a bit more logistically. The biggest physical challenge is that a parabolic antenna, you can put in the terminal, you can measure one full 3D pattern, and you're done. Our pattern, any electrically steered antenna, in theory, has a different radiation pattern for every possible scan angle. And to what resolution do you need to measure that? Do you need to measure down to 5 degrees, 1 degree? Less than 1 degree? How many of those do you report? How many of those do we expect? And we can deliver an operator thousands of patterns. Do we expect them to actually look at that? Probably not. What are they going to do with that data? What is the numbers they want to see from that? How do they then analyze it? And it goes across frequency as well. So our patterns do have changes with frequency. So it's a very multidimensional problem, and the time involved even to measure that many patterns on a regular basis we have to work with. We have our own chambers, but it still takes a lot of time. That's a couple of the challenges that we've seen.
So I know that both Havinder and Joachim have some experience of sort of dealing with the testing challenges. So I wonder if Joachim, maybe you can go first and add to some of those sort of challenges when it comes to testing flat panels versus parabolic.
Yeah, Jeremy is 100% correct. Measuring all possible patterns of in all possible frequencies, and if you then also going to add EIRP and GORT measurements at all of those different angles, you're talking about it's becomes to the point where it's realistic to expect that. I think one of the things that we've been looking more and more into, and what kind of the way forward there would be, is that the simulation that is designed by antenna manufacturers on their antenna, that is the one that you go about comparing with some measurements or critical measurements around, depending on which kind of use cases or which operator that you're working with, and then basically comparing the actual measured results with the simulations themselves, and then making the comparison to actually have some sort of, because then you don't need to have that many measurements, but you can still have quite critical measurements, and you can have a good overall understanding of what the capabilities of the antenna is. So to me, that seems to be the right way forward. I know that Space Force is using this process when they are approving antenna for the WGS network as well. That would be my point.
Great. So Havinder, do you have something to add there on the testing challenges?
Testing for me, I mean, this is putting my, my previous life. Testing starts from, the day you start designing it. I think you start simulating, and then I used to manage some phased array antenna projects and for space applications. And I think the first layer of testing you introduce is when you're doing your breadboarding. Certification comes right at the tail end. Then I think when you start developing your antennas, you'll also start testing in your real world conditions. Where is it going to be applied? Is it going to be in the land, air, or sea, or in the space? And then, because most of the FPAs have got a lot of FPGAs within that, I think reliability is very important, that, there's going to be functional for next 25 years or 10 years or whatever your mean time to failure is, you've been dictated to. Then you've got a lot of, firmware and the software integration, and a lot of FPAs do have clever algorithms nowadays to track satellites, especially from ground, and there's the element of that testing. And then, because I already touched upon FPAs being very power hungry, so their performances could deteriorate if their thermal dissipation is not managed properly. So all these factors do affect your total final testing. I think that the layers of testing need to start early, even though it's on the bench, and eventually it goes into a chamber, which I already said previously that, which will be a terminal testing. And then there are other pressures. This is from my own experience, mostly on like time to market pressure of reducing the test cost, because test cost is a fairly big chunk in any development cycle. So I think there's element of all these challenges, and then obviously you've got regulatory and certification, which we already highlighted previously. So we need to work on those as well. So that's my little justification on the point.
So from your perspective, testing should start right at design stage. I'd love to hear from the others. Do you agree? At what point should we be testing? Angela, do you want to give a view there?
I think it only makes sense that there's testing throughout. Obviously, certification comes at the end, of course. But as a manufacturer's going through and developing an antenna, testing throughout that development, I think would be. I don't think there's any comparable way to continue to get the data needed to ensure that the manufacturer's on the right path for the development of that antenna.
I'm imagining that Jeremy and Joachim, you're both probably in agreement with this point.
Yeah, absolutely. Oh, sorry, Jeremy.
No, please.
Yeah, absolutely. Yeah. I think it's also it's also again application based as well. I think that you start testing in the early R&D phase, and it goes through. You get your certification, and then comes the question: do you test it afterwards, even after deployment? And I think that it's often you want the antenna to be deployed and then it just stands there. But one of the things that we find is, for example, with emergency response, where you at a certain point you deploy a lot of antennas out in the market to respond to a disaster, and then a lot of things are going on and so on, and then afterwards you bring those antennas back to storage again. And as you bring them back to storage, is a great time to see if anything has dented the antenna, anything has made an impact on that performance. So the next time there's a disaster, you don't actually deploy an antenna that is not working as it should be. So that's also a little bit of a different view on it, but yeah.
I agree that testing is necessary. From our perspective, developing a terminal with different principles than is otherwise used means that we were testing from subcomponents and inventing subcomponents of our own all the way up to the entire terminal. Now, that what would have been helpful is if there was a consistent set of standards for testing flat panels available several years ago when we first had our first full-scale terminal, that would have probably adjusted our test plans to be compliant and consistent with the standards, and it would have changed what exactly we measured and possibly how exactly we compared ourselves. We knew that we took several prototypes, of course, to get up to the performance that we would want to get, but it may have colored how we evaluated that data. But regardless, yes, I mean, testing is key to what we've done both in the chamber as well as over the air.
So I'd like to get back to standards shortly, but before, I'd just like to ask Angela to comment on how important getting the right data sets when it comes to these antennas.
It is of the utmost importance to get the right data sets to ensure that the antenna is going to meet the needs of the customer and the environment in which it's going to be utilized. I think, obviously, when you're looking at the data sets, you're looking at that usually tested off of one or two or several antennas. I think one of the challenges that we're seeing is that that some manufacturers are producing antennas with inconsistent performance. So while it's the same, it's considered to be the same antenna type with expected similar performances. We've seen some inconsistency with flat panels as they're coming out and going into utilization. So I think that's in addition to the challenge of getting the right data set initially. Also, when you're looking at the data sets from an operator perspective, being able to absorb and ingest that data in a 3D model is probably one of the biggest needs that we have in the industry. When you're looking at it in a 3D model, you're able to absorb that information into the different orbits and into the different environments that we would be utilizing a specific antenna. How well an antenna performs at LEO, GEO, MEO, obviously it looks very different. But then even to the point of the different operators and how we are designing our satellites. When you look at the GEO orbit, we have satellites that are very traditional, you know, by today's standards may be considered, you know, lower in gain. But we also are operating with very high throughput satellites. And so the needs of what we need from the user terminals in those, even between those two different types of satellites, can look very different.
So how do you, if those are very different, I'm guessing, does it also mean that the data that you need that is different, or is there some commonality if we're looking towards standardization?
I think there is commonality. I think the breadth of the data is pretty extraordinary that's needed. So with that, and also when you look at the amount of data that needs to be produced coming from a flat panel antenna and all the different angles, skew angles and things that could be considered, it's just a very large amount of data. So it's, you know, looking at it, how do we get the right amount of data that gives us the a true understanding of the performance of the antenna without being inundated in that data itself is a very large challenge.
So we have a question from an anonymous attendee that I'd like to just throw in here, which is how do you all see the quality of the product over its life cycle, and how can we monitor that?
You want to go at it? I'll start from, I'm sure, you know, Jeremy and Kim and Angela will have their own viewpoints. Over the life cycle, let's say, take example of FPAs, and they have got a lot of amplifiers at the back, and then amplifiers do deteriorate in their gain over time. So how you would monitor it? I mean, there are certain ways of doing, you know, you're sniffing part of signal out of your outgoing circuit, and you basically recalibrate over time to compensate it for the losses or the loss of gain within the amplifiers. And that's a way of doing things, but I'm sure there are multiple ways of doing things. That'll leave Jeremy and Joachim to touch up on that if they wish to.
Yep, as you mentioned, sensing the output power from the system is the best way. So our terminal, for example, does do live calibration, senses signals coming in and out, and is able to use that to characterize itself. That is our approach to dealing with aging and change in performance over time, as well as over temperature and frequency and the other operating characteristics of the terminal.
So Angela and Joachim, do you want to add anything there?
So, obviously, self-calibration and self-characterization of an antenna is a fantastic way to approach that. It can be challenging when you know, there are times and scenarios where we're needing to perform that characterization over the air. And you're looking, you know, a lot of times we're absorbing data as it relates to the terminal performance through a platform network, and ingesting the data that way. And that is really of looking at how the terminal is receiving the signals from the ground and getting that feedback loop through the network, but also looking at how we're receiving the signals at the hub for those individual terminals. And so when you're looking at it from that environment, there's so many other factors that are playing into that. So the self-characterization of the signal itself prior to, you know, hitting the spacecraft is a much more efficient way of monitoring the performance of the antenna.
Joachim, anything to add?
I don't know, to be honest about it. I don't have enough. I haven't seen enough over time. I mean, from our technology can do it, or you can bring it to a range, but I'm not really sure if unit economics makes sense in at that scale. It all depends on the situation, I guess.
So one thing I think it was Jeremy that you mentioned standards. How do you envisage a way forward? How can we get to a point? What needs to happen to get to a point where we could have some sort of standardization? Jeremy, you brought it up earlier. Maybe you want to start with that one.
You.
Big question.
I suspect that because the applications that terminals in general, not only flat panels, the applications that they go into and the platforms on which they go on and the data rates and mod cods and link budgets that they're expected to hold are all so different across LEO, MEO, and GEO orbits and from cruise ships down to UAVs as very small vehicles. The requirements are unlikely to become standardized, and it would be very detrimental to, I think, the industry as well as the terminal manufacturers to say, here's a G over T and an ERP spec, or here's a fixed number. So performance standardization is unlikely to be the question. It is more important for standardization for me is how can we standardize on which data is used by the operators or by the standardization, the regulatory bodies to evaluate and decide what is the performance of this system and in what modes, in what circumstances can it be used, how much power will be allowed to radiate. Does the power that is allowed to radiate change with frequency, with angle, etc., or is it fixed to nope, it's fixed the worst case? And the decision for what you do with that data it has to be dependent on the customer needs, has to be dependent on the capacity, it has to be dependent on how the operator protects their network and how the operator protects the networks of their neighbors in order to assure that the environment stays usable for all. But from the terminal provider, we can be certain there's always a way to make a terminal safe to be around. We can turn down the gain, we can use a different mod code, we can become compliant. Now that may be challenging to then therefore meet your customer requirements if they've got data rate requirements, but there's usually a way to get on there. But what we want to avoid is having to recapture measurements, measure in a different way or in a different environment or a different set of cuts or a different set of data and or reporting, even if we can take that same data set and we don't have to remeasure, but we have to go back and have our team reprocess it to a custom standard to put into a particular spreadsheet or a particular set of plots. And here's a ream of paper we can set on your desk, and Angela, you'll have a very fun year looking through all our patterns that I'm sure you'd rather avoid. Standardizing the interchange, the format, and the subset of measurements or of cuts, or at least a standard subset that we can capture, that we're sure everyone will use, such that work on one satellite, we know we can take that data and maybe there's options. Maybe this might be measured in a chamber, it might be measured over the air in a far field outdoor range like a satellite catapult, might be measured on a vehicle, might be measured by someone like QuadSat. But how can we reduce the uncertainty of what we should gather, how much we should gather, and what matters and how will it be evaluated, even if the thresholds vary?
Thank you. So, Havinder, do you have a view on that in response, or how we can move towards standardization?
I totally agree with my colleagues already mentioned that the data set is very important, working with the regulatory bodies, operators, the FPA manufacturers, test houses, what they're capable of, because there are certain things we can't do within a confined environment, and that's one of the challenges I'm facing, especially trying to simulate a LEO constellation, and then there's a handover of LEO, and then you're trying to simulate your land, air, and sea motions, whatever. It could be a vehicle, or could be a train, or could be a drone, or could be. So a lot of work is required, but it's a collective effort required within all these stakeholders within the, this whole landscape. It's not one person saying, look, I've done and this is the standard. It's a mutually agreement of those data sets that, we're happy with this. That's the only way we can move forward. And the example is from, I think, the mobile telecom world. I mean, they all, when they all started in GSM world, I think their own way of doing things, but then the standards came later on, and then they found a way of doing things which all agreed to. So I guess that's the challenges we are facing right now with this explosion of LEO constellations and move towards space, and we need to start looking as a collective effort.
So this is absolutely something that we're trying to look into with JSOA and SIG together, and I'd love to get next Angela's perspective on whether one of the challenges I see is getting resources to do this. People are busy, there are commercial pressures. Angela, do you have a view there from an operator's perspective?
As you stated, obviously there are always challenges to identifying the resources that can be dedicated to defining that actual need and getting that into a standardized format. I think it has to start with a generalized agreement of this really is the data set that we need, and that meets our needs at the different by the different satellite operators, and then also at the different orbits. And I think I don't think that we're close in that. I think there's a significant amount of differences in opinions as it relates to that. So I think there's challenges to get to that point.
Joachim, do you have something to add on how we can get to standards?
I mean, so QuadSat have defined basically test procedures based on existing test requirements with satellite operators, and I can see that there is a lot of difference, a lot of similarities, but at the same time there's differences more or less all across. But I don't know, like, if you received a simulation model, Angela, would you be able to then, based on the specific use case, go in and get the data out of that you would need, and if you already knew that you could trust the simulation?
I think that's possible. We would need to look at the simulation model and the formats that it's being produced in. I think from our team that are reviewing all of this data, the 3D model of the performance of the antenna is probably what is the most digestible for absorbing that information and being able to apply that against the different link budgeting tools and things that we have. So that, I think, we've made some effort in looking at the different types of data that can be produced, and that seems to be what we're most effective at interacting with.
So we have a comment on the Q&A that I'm going to read out from Justin Miles, in case anyone wants to respond to this. So Justin says, coming back to standards, I think standard pass-fail criteria and a data package deliverable are important to build and maintain trust between manufacturers, operators, and the customers of both. However, this comes at the risk of limiting innovation as new FPA technologies come to market. Whatever standard is adopted, it needs to adapt and acknowledge the difference between traditional GEO, HTS GEO, MEO, LEO, and even the ASI environment a particular satellite or constellation operates in. Does anybody want to comment on that? You're all just nodding in agreement, so that's great.
I think Justin makes some really good points there, but I think it's very challenging when you look at all of those different factors to take all of that into account and then come up with a standard pass-fail type of situation is where the challenge is. I think, as we've discussed before, coming up with a standard set of data that needs to be produced for these antennas to then be absorbed by the different satellite operators to apply it against their individual bandwidth environments is probably a better way to approach it rather than a pass-fail scenario.
I might suggest that there could be an opportunity for a pass-fail, but that pass-fail is none of the parameters that are currently measured directly. The whole purpose of the standards as written today are prevent interference with another carrier, another user of the same transponder, neighboring satellites. That's the fundamental reason for the regulations, but the regulations assume parameters. They assume that everybody's operating at similar power levels. They assume certain power levels going to the satellite. They assume that neighboring satellites are also at similar power levels, similar frequencies. And so if there's a desire to standardizing directly on the level of a potential interferer rather than your ERP, your G over T, that is probably better, because that is, so we change an ASI, you're alone for 4 degrees. That's going to significantly change the level of an interferer that could appear. If you're on a GEO versus a LEO versus a MEO versus a HEO, the interference sensitivity environment is significantly less. And so, and then what about for a low power terminal? If you have a terminal that is for a very specific purpose, it's running a low data rate, and it's transmitting 35 dB watts, and everybody else in the transponder is transmitting, close to 50. Cross-pole, for example, doesn't matter at all because you're nowhere near to the same standards. You care about what is actually interfering, not looking at a terminal in isolation. The reason why that's probably not done is that's much more individualized, and it depends on link budgets, depends on many things. But when you were bringing some of these more unique flat panels to market and putting some restrictions on them to say, well, this is usable for this set of use cases, it's not going to be applied everywhere. Considering that use case when setting the thresholds, I think, is important. And speaking selfishly, given that I'd like my terminal to get approved to operate on these networks and be used to meet its strengths and in circumstances that avoid its weaknesses, finding the right way to take that apart and apply it.
So we do actually have some more questions from the audience. So I have a question from Kevin. I'm sorry if I'm pronouncing your surname incorrectly, but Kevin Hartono from Bwant in Taiwan. And he says, ESAs use many active components such as BFICs, PAs, and LNAs. How do you measure their characteristics under different operating conditions, such as temperature and humidity? I don't know whether Harvinder or Joachim, you might have some insights there.
I think that maybe Jeremy is the right one to.
Yeah, maybe. Okay.
So I'd say that absolutely the manufacturers are concerned with subsystem tests or component tests, and at the system level, the behavior of the RFICs of your many amplifiers, that should be subsumed completely by the system level tests. The terminal, the antennas need to have their performance and their behavior characterized and constrained in such a way that as a whole, as an entity, it has a definable performance. And yes, it may well be that the system has performance with temperature, performance with frequency variation, and there are dozens of components, even within a parabolic, that have those characteristics, but they all stack up together. So I'd say that is at that subsystem level, component level, that is absolutely solely within the concern of the terminal manufacturer.
Okay.
Can I have a go?
Yeah, please do.
Right, so all these are discrete components, the PAs and LNAs, and I think they should have a application-specific circuitry, and then you test in a normal chamber or for humidity or your temperature cycling. So, I'm not sure what this gentleman trying to extract from us, There's a fairly standard, you need a thermal chamber and a humidity chamber in your lab, basically, which you can do your tests. And you monitor your power levels under those conditions, in the extremes, and the humidity as well as temperature, and then monitor performance. And then, based on your specification, what you're trying to do with those circuits, you basically work accordingly and create your circuitry around that and your system around that. That's my advice to Kevin.
Okay, thank you. So we've got more questions coming in. So Gavin Cox has asked, given that FPA terminals are now capable of active tapering of patterns, has this facilitated smaller aperture FPAs when compared to a parabolic that can still respect EIRP masks and utilize bandwidth efficiently? Who would like to have a go at answering that one?
I've got a very, very short answer to that. I'd say smaller than non-tapered terminals. I don't think there's a firm conclusion across the board that tapering by itself is what makes the difference.
Okay, so Graham Meek from GovSat has also put a comment and a question. So bear with me a minute while I read this out. For us as a geo operator, what we need to know is what's the gain, EIRP, G over T, cross-pole, etc., to calculate accurate link budgets. The FPAs do not fit with the industry standard tools used for link budgets and antenna registrations. There's also a lack of consistency of performance between FPAs from the same manufacturer, and the details are tuned for optimum performance. The information needs to be consistent, otherwise there's no option but to use the worst case scenario. The effect of this is that the customer end user loses confidence and we as an operator get the blame. FPAs are the new kid on the block, and it looks like the manufacturers expect the operators to adapt to industry standards to their products. Unless an FPA is stationary and the tilt angle is optimized so the skew angle is as close to 0 degrees, what choice have we got but to use the worst case scenario?
Was that a statement or a question?
Kind of a little bit of both. Angela, do you have a view on that?
Obviously, it is challenging, and I agree completely with the statement of the inconsistencies between terminals from the same manufacturer, from the same line. We've seen evidence of terminals that are identical in nearly every way externally, with all the same parameters applied, 6 feet apart, and significant difference in performance. So with that, I think those inconsistencies between terminals from various manufacturers makes things quite challenging as we look at the best utilization of these terminals and ensuring that they're operating most effectively on our networks. Some of the other aspects of it, I believe that there are ways that the data can be developed so that we can ingest them into our link budgeting tools, or we could definitely, I think there are enhancements that we can do to our own link budgeting tools that we're utilizing to ensure that we have the ability to utilize these terminals at better than their worst performance. It's going to take some work to get there, and also we're going to need to be able to see more consistency in the manufacturing of the terminals that we're ingesting into our networks. We also will have to be able to ensure that the terminals that these the networks that these terminals are interacting with have the ability to make those adjustments to performance as the environment's changing, right? So if you've got it on a fast-moving vehicle, which changes that skew and tilt, may change that skew and tilt angle pretty significantly, having the network able to interact with that terminal and understand that environment of the terminal itself and make sure that the commands are understood between the terminal and the hub in a way so that it is adjusting the performance and signature of that terminal in real time is really important. We see that today I think there's improvements across the board that can be made within the platform environment to ensure that that's happening more effectively and more efficiently for the future.
Helen, can I kind of give a different, more like advice to the FPA manufacturer, not necessarily Jeremy or Allspace. So this is something I learned very earlier on, that the transconductance, so the active devices are used in the FPAs, right? And they're driven by the transconductance, and which is mostly the wafer to wafer variation, you know, when the devices are made. So if you use consistently all the devices from same wafer, the variation is going to be very limited. So, and the other aspects from my experience is when you're going through the design cycle, making sure that you budget all your tolerances, manufacturing tolerances, you know, all these things are taken into account. And something we both touched upon, myself and Jeremy, was that like a circuitry, or what we call is a sniffer circuit, where you can feedback and you monitor your power levels, and then you can have a consistent performance across the temperature, across the variation of your batch to batch variation. So I don't think it answers Kevin's question, because I don't know which manufacturer they're using for their FPAs. But the point is that aspect of your design, when you start your design, I think these are the things you need to consider very early on.
So, sorry, did you?
I agree completely that consistency is a big effort. We believe that we have a good solution for that in our calibration system, but it is definitely non-trivial. And I agree that for a network that is operating with fixed mod codes, with fixed links, yeah, there's probably isn't much choice but to operate with the worst condition that is expected in operation for a given terminal. That's going to be location and platform dependent. That as part of some of my my other contributions, I'm serving as the chair of the DIFI working group on electrically steered antennas, where a lot of our conversations focus on how can DIFI, or how can DIFI and electrically steered antennas interoperate. And that conversation is focusing primarily on dealing with the fact that the performance of the flat panels changes with time is fundamentally what it is. And it might be due to temperature, might be due to scan angle, might be skew, but at any given moment, the performance of that terminal is changing with time. And how can modems work with that? And the simplest option is, of course, what's the worst case? And there we go. Now you have a fixed system. But coming up with an approach, an industry standard approach, complementary, I believe, to the testing question that Jaso and Sig are talking about, we would like to offer and suggest approaches that allow modems to flex and change and respond and issue appropriate commands to the terminals, such that the user gets to take advantage of all the performance and the capacity that is there on a moment-by-moment basis, but while not breaching the safety lines that are preventing interference. That's not a small request. And we are in active discussions and not yet ready to propose solutions, but we believe that is what is best long term for the industry.
Watch this space. So, Angelo, I think this question is mainly for you, from Gavin Cox, and it's whether operators consider a firmware upgrade to a terminal as a new system, and therefore does that mean need new certification, given that it's the software that dictates the radiation patterns?
I don't know that I can answer that across the board. I think that we at Intelsat have traditionally viewed that as a need to confirm specific patterns as firmware has been updated. So I would assume that in most cases it is viewed that way. I think in the future there are ways to potentially interact with that in a way that some of the self-calibration aspects that some terminals are developing, or some manufacturers are developing, can assist with that. But I'm not sure it covers the need across the board.
Okay. So we've got a question that's actually 3 questions that I'm going to, from Kevin Hartono again. I'm going to try and consolidate it into sort of one if I can. So how do you, when you're looking at testing, how do you account for the fact that a lot of these antennas are on moving vehicles? And I'm aware of the time, so we we may need to do a quick answer on this. So the fact that they're moving, also in a LEO environment where you have to deal with handover, switching, etc. And thirdly, that there's a whole lot of comprehensive testing that's needed. That's a massive challenge. So how do we do all that on this big scale? Joachim, do you want to take that first of all, maybe?
Yeah. I mean, when you're moving, there is a lot of changes, and you can go back and look at the standards that already exist on communications on the move. I think the key thing is that when you reach a non-compliant performance, you cut off your transmission and you wait until you reach compliance again before you start transmitting again. I think that's the only way to do it, and that kind of solves Kramer's challenge there as well, right? If as long as you get to a performance that is not within or not good enough for the customer, you cut off until you are back in a position where you can meet that performance that complies with the operator and what's contractual with the customer.
Havinder, did you want to add anything there?
I can share my challenges, which I'm facing with the facility which we're trying to create for comms on the move, which probably Kevin's probably the answer as he wants. I mean, what we got to create land, air, and sea motions, we've got a motion platform which we recently purchased, and that's got limitations, so we can't do everything, but we can create 6 degrees of movements, angular as well as linear. We're also creating a sensory system where we can do the pointing accuracy, and that's one of the challenges within the SATCOM. When your vehicle's on the move, either you're in a car and you're going up and down the Wales or something, on a bumpy road, or you could be in the middle of a sea on a very kind of windy environment. So we're trying to create those things so that we can achieve a pointing accuracy with the satellite all the time. And then there is a way we're trying to do is create some, again, robotics within the confined anechoic chamber where the manufacturers and the vendors can do their handover algorithm for different satellites. It's not going to be as if you're seeing a LEO, but we are trying to create as much as we can within the space we have. So these are the challenges we're kind of facing, and I think this is what I think Kevin has been kind of trying to touch up on. We're probably one of the few in the world trying to do this thing, and I think where we need a steering from the industry as well to agree on all these motions for the next generation of antenna terminals, and so that we can standardize this process.
Amazing. So I'm aware that our time is more or less up, but maybe we can just, as a last thing, if anyone has, the panel have a last comment on, I feel like there's so much that needs to be done. So where in your view, do we go next to get there? Jeremy, do you want to go first, maybe?
Continuing these conversations that JSOA is starting, I think, is a great first step.
Great. Angela?
I agree with Jeremy. This is a first step. We will definitely need more conversations and really start to look at potential ways to adjust and make sure that we're aiming for the future.
Sounds good. Joachim, do you have more to add?
I agree with the same. I think it would be great if we could, do something practical together. Actually do some measurements, do some tests, and see how it works out with for example a few operators together on one antenna.
Great. And finally, Havinder.
Yes, I agree with my other colleagues. It has to be a very collaborative industry involvement effort, and probably something at global scale as well, because it looks like the questions are coming from different parts of the world, which means people are interested, and more conversations like this, we can start cracking this little big hurdle we got.
So thank you all so much for joining. Thank you to everyone for joining the discussion and for all your questions. If there are questions that remain unanswered, the panel will review them afterwards, and they'll be posted next to the video on the GSOA website, where you'll be able to watch the recording of this if you want to watch it again. The next webinar in the GSOA series is planned for the 31st of October at the same time, and it's New Space, the Reinvention Constant. So make sure you sign up for that. And finally, just thank you to all the panelists for sharing your insights and the great discussion.